Buenos días con todos. Continuando con la programación del día de hoy, es el turno de la doctora Helen Khoury. Voy a dar una breve presentación de la doctora. Actualmente es profesora del Departamento de Energía Nuclear de la Universidad Federal de Pernambuco. Desarrolla actividades de investigación, docencia y extensión en las áreas de dosimetría e instrumentación nuclear, con énfasis en aplicaciones médicas de radiaciones ionizantes. La doctora recibió la medalla Carneiro Felipe de la Comisión Nacional de Energía Nuclear. Así también es honrada como socio meritoria de la Sociedad de Radiología de Pernambuco en el 2019. El día de hoy nos va a presentar el tema titulado Optically Stimulated Luminescence of Calcium Fluoride Doped with Rare Earth Materials. Now in English. She is currently a professor at the Department of Nuclear Energy at the Federal University of Pernambuco. It carries out research, teaching, and extension activities in the areas of dosimetry and nuclear instrumentation, with emphasis on medical application of ionizing radiation. She received the Carneiro Felipe Medal from the National Nuclear Energy Commission, that she is also honored as meritorious partner by the Pernambuco Radiology Society in 2019. Today, she presents us with the theme entitled Optically Stimulated Luminescence with Calcium Fluoride Doped with Rare Earth Materials. Hi, Doctor.
Hello, hi.
Please, you can start your presentation.
Yes, you can see my presentation? Yes? Okay.
Yes.
So first, I want to thank the organizers for this invitation. It is an honor for me to participate in this event and to have opportunity to discuss some of our results related to solid-state dosimetry, in special with calcium fluoride. As you told, I am a professor from Nuclear Energy Department of the Federal University of Pernambuco. I include here Brazilian map because usually the people don't know where is the state of Pernambuco. So it is in the northeast region. Usually the people knows only São Paulo and Rio. And I am here from Recife, northeast region. It is a beautiful city, cut it by river. We have a beach, and here is a photo of my university. So this photo is to invite you to visit us here in Recife. Okay, today we will talk about optically stimulated luminescence, dosimetry, and some materials. So what is OSL? OSL is an alternative to thermoluminescent dosimetry and field dosimetry. It is a recent method that is introduced and has a lot of advantages related to thermoluminescent dosimetry. And the principle of their operation is similar to the TL. The difference is only in the way in which the electrons are freed from their traps. The OSL advantages are, I here relate some of them. First of all, allows multiple reading of the dosimeter. This is nice because you can repeat. It is possible to read TL signal after OSL, and the measurements are carried out at room temperature. So who is familiar with the TL, we know that we need to use nitrogen to reduce the temperature of the material of the photomultiplier. All of this is a cost, and when it's possible to do the measurement at room temperature and repeat it, it is a good option. For this reason, the OSL dosimetry are increasing. At the moment, the commercial dosimeter is the aluminum oxide doped with carbon. And more recently, we have some materials with beryllium oxide. So it is a field, a big open field to study new materials and the response of new materials that can be used for radiation dosimetry. And in this direction, we are studying the calcium fluoride. Well, what is the idea? What is the main concept of this luminescence dosimetry? We know when we have a crystal with some impurities, we have some levels, trap levels in the region of prohibited region. So when ionizing radiation interact with the crystal, the electron receive energy and move from the valence band to the conduction band and can be absorbed in the metastable states. If the electrons stay storage in the traps with the metastable states, we need to give a stimulation to move this electron to the conduction band and then to recombine with the combination centers. This excitation, we can do it heating the material, and in this case, the temperature give energy enough to the electron move from the trap and then recombine in the center of recombination. And in this case, emit light, and this light is proportional the quantity of the trapped electrons. And this method is known as thermoluminescence. Instead of heat, if we use a light, the phenomenon is referred as optically stimulated luminescence. So in optically stimulated luminescence, we use light to stimulate the electrons that were trapped in the metastable states to move and then recombine, and the quantity of the light emitted for the electrons are proportional to the dose received by the crystal. And using this intensity or measuring this intensity, it is possible to have an idea about the dose received by the crystal. So as we thought, both OSL and TL are very similar. The only difference is the way the electrons are freed from their traps. Okay, today I will talk only about OSL and related to the calcium fluoride. In both equipments, TL reader and OSL reader, we need an equipment to measure the light emitted by the sample. In this case, it is a photomultiplier. When the sample irradiated is heated, it emits light, and this light produce in the photomultiplier electrons that are multiplied in the denotes inside the electron and finally produce electric signal. And the intensity of this signal is proportional to the light incident in the photomultiplier window. So there are a relation between the light incident to the photomultiplier and so the light emitted by the material. And this relation is associated with the dose received by the material. When we heat with the temperature and acquire the signal, the intensity of the signal, we can obtain this glow curve. The glow curve represents the light emitted by the crystal as a function of temperature or heating time. So we see here some peaks because this material has different levels and need different energies to move the electron from this level than with this level. So depending on the energy and the temperature received, this move the electron in different levels, and this gives us different peaks. This is the glow curve of the TL materials. On OSL, the curve is totally different. In the same case, we have the excitation, the stimulation by light, the electron move and recombine, emitted light, and this light emitted is measured by a photomultiplier. And the curve we obtain with the time is like this. We have high intensity in the beginning and decrease as the trap are emitted the electrons. The equipment are also similar, but have some details. See, to make stimulation of the dosimeter, we need light. This light should be blue or green or infrared. And this light can come to the photomultiplier and produce signal. So we need to avoid the influence of the light used for the stimulation in the response of the photomultiplier. For this reason, in front of the light source, we have filters. So only light with well-defined frequency is emitted and excitate the dosimeter. We will see later that depending on the material, the response will be better with infrared or blue. And the light emitted by the dosimeter is emitted in one frequency or part of frequencies. So we here use another detection filters to only allow that the light emitted from the dosimeter will be incident to the photomultiplier window. With these two types of filters, adjust these two types of filters, it is possible to reduce the influence of the light source on the response of the photomultiplier and increase the efficiency of the photomultiplier to receive the light emitted by the dosimeter. Well, we have three modes of operation of the OSL system. The first one, and more used, is continuous wave OSL. In this method, we stimulate the sample and at the same time measure the light emitted by the sample. It is continuous. In POSL, we have a pulsed stimulation. And LMOSL, linearly modulated OSL, we have a stimulation that changes with the time. I will try to explain here. Here, in pulsed mode, we have stimulation, and at this moment, when we have the light stimulation, the photomultiplier has a shutter in front of it, and it's not measuring the light. After stop the stimulation, the photomultiplier reads the light emitted by the material. Next stimulation, and so on. So during this first stimulation, the material is emitted light, but this light we are not measuring. So in this method, we lose this first part of the emission of the material, but we measure this second part, that is the decay after the stimulation. Here you can see the photo of one equipment that we constructed in the lab, and you can see this level is the light, the background light, the influence of the light due in the photomultiplier, and here is the response after the stimulation of the material. In general, we associate the area of this curve with the dose received. And in the in the continuous mode, we have all this information, but we measure all the time. So it's possible to measure in the beginning. Many times we have increase and then decrease, depending on the material, okay? And in linear increase, we have the stimulation with different intensity with the time. So this will give us this type of curve. We use this method when we want to know if there are more than one level in the trapping levels. But usually we use SW or pulsed OSL. Okay, so what is important? See, the material that was irradiated now after stimulation emit a light. But this light has a frequency, and it's important that the wavelength of the light emitted by the material are in the same region of the sensitivity of the photomultiplier. So study the emission spectra of the materials is very important to see if these spectra are in the region of the photomultiplier response. So we know that depending on the photomultiplier, the efficiency, quantum efficiency, depends of the type. For example, this photomultiplier, the best response is in this region. This is large. So if I am using a material, for example, that emit the light in blue, and my photomultiplier is this one, the photomultiplier will not see my light because it's outside the region of its good efficiency. So it is important to have the coincidence between the response of the photomultiplier and the light emitted by the material. So many times we are studying materials and say, no, this material is not good, but it's not true. We have to say it's not good with this type of equipment, with this type of photomultiplier, because we have to study its emission spectra and see if the emission spectra is outside or not the response region of the photomultiplier. So now I will try to show you some results about calcium fluoride. As you know, calcium fluoride or fluorite, as is known, we have it in the nature, and we have with different colors. And naturally, we know that calcium fluoride presents a TL response. But what happened? Depending on the origin of the calcium fluoride, we have different response because there are different impurities in the samples. So to produce dosimeters to be used for medical applications or industrial application, it is not adequate to have a material where you don't have a control about the concentration of the impurities and the type of the impurities. For this reason, we and other researchers try to produce in laboratory calcium fluoride doped with rare earth materials. And this is what I want to show you some results and the effect of the type of the dopant and the concentration of the dopant and so on. Well, there are many methods to produce the material. In our case, we use the combustion synthesis. This synthesis is based on the heat after a redox chemical reaction. In this case, what we use this chemical reaction to produce a heat material and then produce the reaction. This method is produce highly homogeneous materials with nano-sized grains. It's not necessarily high temperature annealing. It use a relatively simple equipment, produce a high purity products. It's a low cost and it's fast. For this reason, we are using it. And in our case, how we produce the calcium fluoride doped with different materials. First of all, we use calcium nitrate, mixed with ammonium fluoride and urea. Urea is used as a fuel. And depending what we are preparing, we use dopant or europium, terbium, cerium, thulium, and depending on the material we want. So first of all, we mix these materials and try to evaporate the excess water and put in hot plate for a few minutes for evaporation. After that, we introduce this material, we transfer to muffle furnace at 565 centigrades, where intense flame type combustion occurred. So we have this boom, okay? After minutes, we have the combustion, and this combustion produces the powder. That this powder, after that, will be pressed in pellets with 6 millimeters diameter and 1 millimeter thickness. Here you can see some samples of the pellets. Okay, with this material, we don't use binder because it is possible to obtain a good mechanical stability without binder. Some materials need to use binder to have a good mechanical stability. After produce the pellets, they were sent. We put in a temperature 400 centigrade for 8 hours. Then we have samples that we study and characterize for radiation dosimetry. Okay, first of all, we want to see if the powder produced is really calcium fluoride. And here you have an example of X-ray diffraction of calcium fluoride with thulium and compare it with the standard ICSD. And you can see that it is the material produced is calcium fluoride. Okay, the pattern of the material is similar of the standard one. Then we study the emission spectra. So how we study the emission spectra? We have an equipment that measures the light emitted by the material and give the relation of this light with the energy. Here you have a spectra for calcium fluoride. Here we have two, with doped with thulium. You see we have different regions of energies. If we change to dysprosio, we have another energies. And here you have an example for different dopants. Erbium, cerium. Look, cerium emit here in this region. Thulium is in the region of the blue color, and this is the best one for the photomultiplier, where we have the high efficiency of the photomultiplier. So depending on the dopant, you will have different materials, okay? Different emission, okay? And here you can see the influence of the dopant on the emission spectra. You see cerium, terbium, dysprosio, and here dysprosio has another one. So look there, and looking the photomultiplier we have in our equipment, we can say, okay, this is possible to use this material or not, okay? So we tried to study the response of the calcium fluoride doped with thulium using stimulation with blue light and infrared light. What we observed that with blue light, the response is very, very small, but for infrared is very high. This is fantastic because there are a few materials, OSL materials, that has a response in infrared region, stimulation. And on other side, stimulate with infrared light, it is better because the photomultiplier usually don't see the infrared light. So reduce the influence of the light source stimulation on the response of the photomultiplier. So we studied with thulium, and here we have the comparison of the limit of calcium fluoride with thulium using blue OSL and using infrared. With blue OSL, our limit detection is 1 milligray because the sensitivity is small. But for infrared, it is 0.1 milligray. This is very important because in this dose vision, we can use this material for personal dosimetry and open opportunity to use for individual dosimetry instead of TLD that usually is used in dosimeters, or aluminum oxide that is used in commercial materials, okay? We have a laboratory, radiation protection laboratory that make the service, individual service, monitoring service, and one of our goal is to use this material produced by us in these dosimeters, personal dosimeters, okay? Here you have the response of the OSL intensity with the dose using blue and infrared stimulation. So you can see, as I told, with infrared stimulation, we have high sensitivity compared to the blue stimulation. Look, this is for fluoride, calcium fluoride with thulium, but you will see that using another dopant, it is not necessary. We have a good response with blue. So depending on the dopant, you have different response of the materials, okay? And we studied also the TL after OSL measurement. Why we did that? We want to understand if the light emitted in OSL is from the same levels, rep levels that it is emitted for TL. So first we read OSL and then we read TL. But what we did, we first hesitate with the small time and read TL, and then increase the hesitation time with OSL. And what we see that OSL increase intensity and TL decrease. So finally, we decide that this behavior indicates that the OSL and TL in this case of material are related with the same levels. it is not necessary for all the materials, but in this case, it is related with the same levels. Okay, when we change the dopant for cerium, what we see that for BSL, or blue light stimulation, the response is higher than with infrared. For blue, we have higher response than with infrared. It is interesting also because this is another type of material and can be used for other applications, okay? One point that I want to show you is the influence of the percentage of dopant. Here I'm showing with cerium, but we did the same study with the thulium, dysprosium, and so on. And depending on the dopant, this concentration change. For cerium, the best concentration of the dopant is 0.2. So all the materials of calcium fluoride we prepare with cerium, we use 0.2% of the dopant. And in this case, you have here the curve of cerium with the calcium fluoride with cerium in comparison with the response of aluminum oxide. You see, it's very small compared to aluminum oxide, and the same for the blue. But both blue and infrared present a response and show that it's possible to use calcium fluoride with cerium dopant for dosimetry. Because you have to remember that depending of the use of the material, it is important to have low or high response for the dose. For example, for some industrial applications, we need dosimeters for high doses. For medical applications or individual dosimetry, we need low doses. So you need to have different type of materials to attend the different necessities we have in the applications, okay? What we did also is to study the influence of codopant, not only cerium, but cerium and lithium. So in this case, we use two codopant. We use cerium and lithium. And what we observed that the response is very high, including higher than aluminum oxide. You see, aluminum oxide is the commercial one, and the response with the codopant is higher than the aluminum oxide. And this response is infrared response, stimulated response, okay? So we tried with terbium and also see that with the codopant, terbium and lithium, we obtained a very high response, very high compared to aluminum oxide, and better than we use only with terbium. The intensity is also associated with the emission spectrum. Remember that terbium also emits in the region of blue light. Here you have a table with the comparison of the sensitivities of samples of calcium fluoride doped with the cerium, lithium, terbium, and so on. You see that with codopant, terbium, and lithium, we have the highest sensitivity, double than the aluminum oxide. And cerium, only cerium, it is the lowest one, okay? So these studies allow us to select the best material we can use for the applications or radiation applications that we want. But another point important in dosimetry is the fading. How many times the material stay with these electrons in the trap levels. So what we observed that in case of cerium and in case of terbium, the fading is very high. You see here after 2 hours, the reduction was 65%. This is not adequate, for example, a dosimetry for medical applications or individual applications. So this limits the application of use of this material for medical applications. But it can be used, for example, for nuclear forensics or safeguards. It is now world wants to have sensors to measure one unplanned or undeclared movement of sources, of radioactive sources. And we can use this material with high fading, put it in a miniature readout and in a portal monitoring. And when the source passes, irradiate the material, and then we have the signal and the decay signal. And with the decay signal, we can have an idea when the source passed from this portal. This is one application we are proposing for this material that have a high fading. Okay. On the other side, we studied the response of the calcium fluoride with thulium for electron beam radiation processing dosimetry. You know that for industrial applications, they use electron beam, and the dose is very high, and the energies also are high. And so we wanted to study if it's possible to apply our dosimeter for these applications. So we irradiate in IPEN, Instituto de Pesquisas Energéticas e Nucleares, from the National Commission of Energy in São Paulo, and irradiate. Here you have with different doses for electrons with 1.5 MeV. And you can see that the response increased with the dose as expected. And we have for two different rates, 2 kilograms per second and 8 kilograms per second. You see that we have different response depending of the dose rate. But it is linear in the range from until 6 kilograms. And after 6 kilograms, we observe in all the rates saturation. And this indicates that it is limited its use until 6 kilograms with electron beam used in this industrial applications. Okay. And after the irradiation, we measure the TL. And you can see here is the TL response, only TL. And here is the TL after the OSL measure. You see, this first peak of TL disappeared because this peak is responsible for the OSL response. And part of this peak is residual in the TL. So with this, we can use also to measure OSL and TL and organize a calibration curve with TL and have two measurements for the same situation. This is important because sometimes you measure, you had a problem and you want to repeat, and if you lose the signal, you can't repeat that situation. Okay, so in conclusion, we can say that the combustion synthesis is a adequate method to produce a calcium fluoride doped with rare earth materials. The calcium fluoride with thulium presents a response, IRSL response, approximately 3 times higher than blue OSL. The minimum measurable dose of BSL of calcium fluoride with thulium was found to be 1 milligram, and for infrared OSL was 0.1 milligram. And in this case, it is suitable for personal radiation monitoring applications. Despite being dose rate dependent, the use of calcium fluoride with thulium for electron beam processing dosimetry is possible. And using cerium as dopant shows material with a similar response both for BSL or infrared OSL. And the use of lithium as a codopant can increase the response of calcium fluoride doped with terbium and with cerium. We have a lot of things to study. It is an open research material, and also to study its application and see the possibility to produce another material, a commercial material, to be used in medical applications. Okay, so I want to thank again for this opportunity, and also I want to invite all of you. we are organizing the first Latin American Congress on solid-state dosimetry and radiation measurements that will be virtual way. This year, unfortunately, need to be virtual during the period 13 to 17 September. Before this period, from 8 to 10, we will have a school with McKeever, Anatoly, persons from solid-state dosimetry that will give the classes. Our idea is to motivate young researchers for the area of solid-state dosimetry, increase the groups that are working in dosimetry in our region, Latin American region. And here is the site of the conference and the contact, and I hope you can participate and divulgate this conference. So again, thank you. And if you have some questions, I'm here to try to answer. Thank you.
Thank you so much, Dr. Helen. Si alguien tiene alguna pregunta, por favor, puede levantar la mano o activar su micro. Any question, you can up your hand or activate your micro, please. Medina, puedes activar tu micro.
Yes, okay, thank you so much. Doctor, hi, good presentation.
Puedes hablar en español, no hay problema, voy a intentar te contestar en portuñol, ¿qué tal?
Ok, muchas gracias.
Así que nos sentimos todos mejor.
Ok, yo tengo una pequeña consultita. Estas aplicaciones de las que estaba mencionando acerca del calcio y fluoros, ¿pueden ser diseñadas para poder utilizarse en el campo médico, de repente para la conservación de algún tipo de material orgánico? ¿O de repente por ahí no va un poco la explicación? O...
Como para conservación? ¿Es para medir la dosis que se utiliza para conservación o como material que se puede conservar? Porque esos son sensores para medir efectos de radiación. ¿Este material médico sería esterilizado por radiación? ¿Es eso?
Bueno, claro, lo que pasa es que anteriormente también presenté una charla donde estaban hablando acerca de la dosimetría que era emitida hacia una, digamos, hacia material orgánico, solamente lo definieran así, por eso que sea más que todo la consulta.
Bueno, yo no sé decir, porque en verdad no sé, no lo utilizamos como material orgánico y bueno, no lo sé, no entiendo cómo se utilizaría para conservación de material orgánico, es eso.
Ok, disculpe en todo caso, muchas gracias.
Perdón, es que no conozco, pero después si quieres podemos hablar más, pero no entiendo bien.
Ok, listo, muchísimas gracias.
Acá hay una pregunta, si los materiales sintetizados tienen algún tiempo de vida por el uso. No tienen. Lo importante es que después que se hacen los pellets, que tenga una rigidez mecánica. Es igual el TLD de LIS, el TLD 100, que se utiliza para dosimetría. Tú puedes hacer la irradiación, hacer la lectura, después tratar térmicamente y de nuevo leer sin problema ninguno. Solo tienes que garantizar la rigidez mecánica para que no se pierda la masa del material. Solo eso, ¿tá? Y no hay problema ninguno. Y el tamaño de las muestras, la frecuencia emitida no. El tamaño no cambia la frecuencia. El tamaño de la muestra cambia la sensibilidad. Si tengo un pellet de mayor tamaño, tengo más sensibilidad o menos sensibilidad. Pero no la frecuencia. La frecuencia depende del dopante y también de la dimensión del polvo. Es que no hablé para ustedes. Es que hicimos un estudio para saber el tamaño, el grain size, el tamaño del grano que tenemos que utilizar después que el polvo es producido. Y identificamos que entre 75 micro a 100 micro es lo mejor. Entonces, después, antes de hacer el pellet, como se dice, seleccionamos estas dimensiones de granos para hacer los pellets, porque presentan la mejor respuesta.
Doctora, Doctora Khoury,
Sí.
a ver, perdón, ¿puedo hacer la pregunta? Doctora Khoury, ¿es posible usar estos elementos dosimétricos en campos de radiación mixta, en campos mixtos?
Sí, sí, estamos trabajando, pero no fluoreto de calcio. Nosotros estamos trabajando con borato de litio. Entonces, se puede producir con litro 6 y litro 7, litio. Entonces, uno mide gamma en neutrones y otro solo mide gamma. Y entonces, la idea es poder medir en campos mixtos y saber cuál es la dosis para gamma y para neutrones.
Ah, perfecto, muchas gracias.
Nada. Es un campo muy bonito. No sé cuál es la área de trabajo de ustedes, pero esta área de materiales es muy bonita y muy abierta. Se puede, miraste que poniendo codopantes cambia la respuesta. Hay mucha cosa que depende de alguien de la área teórica que pueda entender lo que pasa. Nosotros, como somos experimentales, lo hacemos un poco como voy a decir, empírico. Y lo testamos y identificamos la mejor forma, pero tenemos un grupo que trabaja con la parte teórica que intenta explicar por qué están ocurriendo estas cosas con los niveles de energía del cristal.
Doctora Khoury, entonces es una gran oportunidad de poder contactar algunos docentes y estudiantes de la Universidad del Callao con su laboratorio para poder buscar lazos de amistad y colaboración experimental o teórica.
Perfecto, perfecto. Es un gusto para nosotros. Nosotros tenemos un curso de maestría y doctorado y tengo recibido mucha gente. Tengo estudiantes de Colombia, Ecuador, Cuba, que vienen y hacen la maestría con nosotros y después vuelven a su país y intentan empezar en su país el trabajo. En Perú también hay mucha gente, y mucha gente de Perú va a São Paulo con el profesor Shigeo Watanabe. Pues tienen mi email, o quiere que yo ponga en el chat. Puedo poner en el chat.
Le agradecemos mucho, doctora Khoury.
A sus órdenes. A quien quiera, ya está en el chat.
Muchas gracias, doctora. Si alguien tuviera alguna otra pregunta. Me parece que no, eso sería todo. Muchas gracias, doctora.
Muchas gracias, digo yo, y fue un honor poder participar de este evento. Muchas gracias.
A usted por su presencia. Gracias.